Hi. This one's really interesting. There's actually lots of multiple answers, an infinite number of answers, and we're going to write them all. No, we're going to do one of them that would seem fairly obvious, and we're going to go for one that isn't quite as obvious, and I just want to show you the different things that could happen in this process, and based on the way you are hard for me to say, based on the way that you are interpreting this. So let's just go for the obvious first, and the obvious would be that delta x is 2 over n, which means that delta x is 2 over n, the width of our rectangle is 2 over n, then b minus a is equal to 2. So the width of this interval is 2, just 2, right? So from here to here, it's 2. Well, knowing that, I need this to represent a delta x in here. So what I really have instead, I'm going to erase some stuff, and you want to scribble some things out on your paper, feel free. I really want this to say 2 over n. That's what I want. But I did have 4k, so I need to keep my 4k. So I really need 2k times that 2 is going to give me 4, right? So again, we're dealing with an interval with a width of 2 from here to here. I don't know the function, but as I look at this basic structure, I'm seeing kind of what my input would be. And in this case, this is similar to what we had in the last problem, the loud marker. This right here is my input. Starting with the left side, going all the way, starting with A plus a little bit more based on the width of that rectangle. And in this case, this is our input. That was our input. This is our input. Okay, so we have an input of k times 2 over n. And so you're thinking, well, what about this 2? It's like I'm multiplying my input by 2. On the previous problem, we had 1 plus 2 times all your input. Okay? On the very first problem, we had the cosine of your input. Well, in this case, we have 2 times your input. We can tinker with that. We're going to come up with some other options and possibilities of what could happen here in a minute. But for now, this is what we really have. It's just 2 times your input. So let's run with that idea. If I have 2 times my input, then my function actually is just, well, 2x. And we can also kind of look at this input as this structure, and we realize that we truly have, just looking right here, from k 2 over n, k times 2 over n, is this, which means we don't have an a, which means we start at 0, and we end at 2. We start at 0, we go up 2, so that's it. That's it, okay? And that's one of the things we could do. Let's do another one. All right, let's jump back to the very beginning. Back to the beginning again. And it was 4k over n. Now, if you want to get technical, you can multiply a whole lot of stuff together. So I'm going to take just this portion right here, and I'm going to tweak it a little bit, and I'm going to turn this portion into 8k times 2. I'll make that 8k over n, and then 1 over n. This is equivalent to that, right? They're the same. So I could just kind of start here, and then I would say, well, all right, that's fantastic. What I truly have then is, just using this idea, a width of 1, and therefore this should start somewhere and end at 1, and this is really 8k times 1 over n times 1 over n. Looking at the structure, 1 over n, it's our delta x. 1 over n is our delta x. There's our k. And then everything else is what we're doing to our x. I'm multiplying my input by 8. So, wrong color, but 8x, starting at 0, ending at 1. Wait a minute. Is that the same thing? It is. It is, it is, it is, it is. Now, this may not mean a thing to you yet, but when we cover this, you're going to say, whoa, those are the same thing, right? So just wanted you to see that. Even though there's a glare, there we go. Tilt it to where you can see it. Those are the same thing. All right, may not mean much out of context about what those truly mean. They do represent the area bound between this line and the x-axis from 0 to 2, or this line and the x-axis from 0 to 1. So we have a steeper line with a narrower interval, or a not quite so steep line with a wider interval, and we get the same area. Just a different interpretation of the same thing. Okay, all that, I'm going to erase this bottom one. All that was all well and good. Let me go back to the original. We had what, 4k over n times 2 over n? Yeah, that was the original. And now we're going to do a left Riemann sum. We'll do both options for this. So again, this was a right Riemann sum. Right Riemann sum. Pronounce it out loud, it goes "ers." And then a left Riemann sum would be, and we'll use blue again, it would be the limit as n approaches infinity. Okay, left Riemann sum would start all the way to the left. So let's actually start counting up our rectangles at the 0th rectangle. So basically the leftmost point and then plus 0 rectangles. So we could do it that way. And it would be the same structure right here. 4k in 2 over n. Or, and you could put an equal sign there, or it is the limit as n approaches infinity. Okay, let's start at 1, we'll go to n. And we're going to do the same thing, but I really do want to start counting my rectangles at 0. So instead of k, I'm going to put k minus 1, which resets it back 1. We've done this a couple times before. I just want you to be aware of that, because I have seen some multiple choice questions that'll say, which of the following is a left Riemann sum? And when I looked at it, I was like, whoa, I always taught this with a right Riemann sum. So I want us to have this ability to kind of translate and realize that left Riemann sums go all the way to the left, meaning I'm at the left plus 0 rectangles or 0 rectangles, whereas a right Riemann sum is at the left plus 1 of my little rectangles. Good to know. Some good patterns to know. Okay, one more after this one.